This is part 3 of the lecture covering one-dimensional motion with constant acceleration. In part 2, I performed an example problem involving an accelerating rocket ship. Let's immediately now move on to the next example. Take a moment to copy it down in your notes. It involves the car that is slowing down. Let me go ahead and read the problem to you. A car initially traveling at 30 meters per second slows down to 20 meters per second over a distance of 50 meters. What is the acceleration and how much time elapsed? Once again, I'll be using the basic methodology for solving a physics problem to approach this example here. So let's begin by drawing a basic diagram. Okay, so very simply, here is the car to begin. Here is the car to end. Once again, even though it doesn't explicitly say so in the problem, let's just automatically assume that the car begins at the origin. So then therefore the initial position x0 is equal to 0. Okay, now the car is initially traveling to the right-hand side at 30 meters per second. That's the initial velocity vector. So right here, for example, like so, is the initial velocity to the right-hand side of 30 meters per second. And at the end of the problem, the car's final velocity to the right-hand side is at a lesser magnitude. It's at 20 meters per second. Make sure that you draw the final velocity vector here smaller than the initial velocity vector. So right here is the final value of 20 meters per second. Okay, and then we're given the displacement here as 50 meters. That's the magnitude of the final position vector of the car. That's the distance traveled. So right here is the final position vector with a magnitude of 50 meters. Okay, now we have two unknowns, the acceleration and the time. Now let's immediately begin to apply the relevant equations. Like the rocket problem from earlier, this is a situation involving one-dimensional motion with constant acceleration. So then therefore the same two kinematics equations apply here. As I write down these equations, I'm going to immediately plug in the zeros. Only one thing, however, is equal to 0 in this example, and that's the initial position x0. So then therefore the two equations become the following. Here's my position equation. Notice I'm immediately writing x0 here as being equal to 0, and then right here is the velocity equation. And now what I have here is a system of two equations and two unknowns, and now I have to algebraically then solve for those unknowns. Here's the process for doing so. What I'm going to do is take the velocity equation and first of all solve it for the time t, and then I'll plug it into here and here in the position equation. When I do, I'll only have one unknown left, and that's the acceleration, which we can then solve for. So let's go through this algebraic process. So to solve for the time t, first of all, move the v0 here to the other side, like so, and then divide by the acceleration a, like so. And now I take this expression for the time, and now I plug it into right here, into my position equation. So plugging into the position equation now, we have time t here, like so. And then plus 1/2 a times the time squared. Like so. And now as you can see, this begins to get a bit messy algebraically. So let me go ahead and take you now through the algebraic steps. So first of all, in the second term, I can go ahead and do a little bit of canceling. I'm going to go ahead and cancel out an a here and here, like so. And now in the first term here, let's go ahead and multiply everything out. So position x is going to be, first of all, v0 v over a, and then minus v0 squared over a. And then in the second term over here, all the terms are going to have a 2a in the denominator, but here in the numerator, I have to go through the FOILing process that you have seen in mathematics class. So I first of all have v squared over 2a, like so. And then I have here v times a negative v0, but then there is a second v times a negative v0. So there's two of them. So minus 2 v0 v over 2a. And then the last term is negative v0 multiplied by itself, so plus v0 squared over 2a, like so. And now at this point, I can go ahead and start to simplify. So first of all, in this term, these 2's cancel here and here, like so. And then I have over here to the left a positive v0 v over a, and then right here is a negative v0 v over a. So those terms drop out completely. Here and here. And now with the terms that remain, take a look at those terms. Notice that I can get a common denominator between them. That common denominator between these terms here, here, and here is 2a. So let's go ahead and add a 2 here and here, such that I can now get a common denominator between those terms. And now we're left with the following. The position x is now as follows, where 2a is the common denominator for the three terms. So now when I add up those three terms, I first of all have here a positive v squared in the numerator. And now here is a minus 2v naught squared plus a positive v naught squared. That then leaves me with a negative v naught squared like so. And then at this point, what I'll do is a little bit of cross multiplying in just a moment, and I'll then just solve for the acceleration a. What I'm actually doing here, however, in the context of this example, is I am deriving for us what is called the third kinematics equation. The third kinematics equation is nothing more than the first two kinematics equations algebraically combined together with time eliminated between them. That's what I'm doing here. This right here is the third kinematics equation. However, it's usually written in terms of a v squared. So then therefore here, off to the side, let me go ahead now and write the third kinematics equation. Like so. What I've derived for us, however, for the third kinematics equation was with the assumption that the initial position x naught was equal to 0. If x naught was not written as 0, it basically gets dragged through this process algebraically. Ultimately, it ends up as the following in the equation. Like so. Once again, this expression right here is known as the third kinematics equation. It's very useful in a problem such as this when both the initial and the final velocities of the vehicle are given. Do you have to derive the third kinematics equation every single time that you do a problem? Absolutely not. You could just go ahead and directly use it once you've seen the derivation of it, which I have done for you here in the context of this example. So as we'll discover over the course of the year, the third kinematics equation in different situations is actually quite useful. Okay, now let's just go ahead and continue with the problem itself. Let's back up to this step here. Now I'm going to go ahead and cross multiply and solve for the acceleration a. Like so, and at this point I'll go ahead and plug in my numbers, and when I do, the dimensional analysis, which I will not perform here, will give us an acceleration in terms of meters per second squared. But now let's just go ahead and plug in our numbers. So first of all, in the numerator I have right here 20 squared, so 400, and then minus 30 squared, so minus 900, and then divided by 2 times the final position. The final position, remember, was given as 50 meters. So 2 times 50 is equal to 100, and this ends up being negative 5 meters per second squared. So what does the negative sign mean about the acceleration vector? It does not mean that the object is slowing down. Instead, it means that the acceleration vector points to the left-hand side. Here's how you can see that. Recall the following tail-to-tip method of vector addition of velocity. Initial plus change is equal to final. So take a look at the velocity vectors for this car that we have here up on the top board. We first of all have the initial velocity like so, and then right here is the final velocity like so. Using the tail-to-tip method of vector addition on this diagram, where is the delta v vector? It's right here, like so. Notice that it points to the left-hand side. That is, initial plus change is equal to final. The delta v vector pointing to the left-hand side means the following. Recall that acceleration is change in velocity with respect to time. The delta v vector's direction is always the same as that of the acceleration vector. So if the delta v vector points to the left-hand side, the acceleration vector points to the left-hand side. That's what the negative sign means here in this example. Now, in this example, when the car is slowing down, we sometimes use the word deceleration to describe such a situation. That's perfectly fine to do so, but the word deceleration is a context word. It does not have a mathematical definition. We still have here, however, an acceleration because the velocity of this car is changing with respect to time. It's okay to say the word deceleration, but just keep in mind that it's a context word. It's not a mathematical description. Here in this case, the car does have an acceleration because the direction and magnitude of the velocity vector is changing with respect to time. The delta V vector here points to the left-hand side. The acceleration vector points to the left-hand side. That's what the negative sign means. So right here is the acceleration vector, like so. And now that I've solved for the acceleration, the remainder of the example is easy. That is, we need to find the time. So the time t, which remember from earlier was v minus v naught over a. And now we plug in our numbers. 20 meters per second minus 30 meters per second. We'll get a negative number here in the numerator of the expression, but now also in the denominator of the expression, we have a negative number as well. All the negative signs will work themselves out. So just to be certain, let me go ahead and calculate this out on my calculator. So 20 minus 30 in the numerator and then divided by -5. This then gives us a total time of 2 seconds. So once again, it's perfectly fine to use the word deceleration as long as you use it in context. Let me conclude this particular portion of the lecture with this example.